welcome back. So, so we ended with basically showing this series of implications, right? That we can start with any dual mode trapdoor claw-free function, use that to implement this idea, or implement this oblivious state preparation protocol, and then show that that suffices to do blind delegation of arbitrary quantum computation, okay? So what I want to start with now is then how do we go ahead and construct this object, DTCF, from a standard post-quantum assumption, namely LWE, okay? So in the first couple of days here, we saw a lot about LWE, so hopefully the techniques here will be pretty recognizable, okay? So before using LWE itself, the basic idea for how to do this is to fix some parameters. So let's let Q be some large modulus. Let's not worry so much about what it is. M is a little bit greater than N. And let's just sample a uniformly random matrix A, so kind of a tall, skinny matrix A that's M by N, okay? And I guess I should say that if we sample A this way, it's, with overwhelming probability, it's going to be full, like a rank N matrix, right? And then let's also sample, let's imagine sampling a random vector in the column span of A. Okay, so I'm going to let V be this vector. Okay, and I'm going to use A and V to define a candidate dual mode trapdoor claw-free function. Okay, so what are my two functions? Remember this DTCF comes along with two functions, right? A 0 function and a 1 function. And, suppose I just define so the function itself is going to be determined by A and V. And then my 0 function, I'm just going to say on input X, which is a vector in Z Q to the N, I'll just output A times X. Okay, so this function is just basically evaluating this linear map defined by A. Whereas my 1 function, I'm just going to be the same thing, but I'll add V to it, right? So the thing to notice about this is that on the domain of vectors in ZQ to the N, this pair of functions have exactly the same image, right? And you can see that just by writing like AX plus V is actually equal to A times X plus S, right? So the image of both of these functions is just the column span of A, right? Okay, so that's good. We have, in some sense, we have some correctness in terms of like these two functions sharing the same image. We want to make eventually this yeah. Mm-hmm. Am I putting what? V is a ZQ to the M. A is tall. Yeah. Okay. Good. Yeah, so A is a tall matrix. Yeah. So, okay, to make this initial candidate dual mode, what we can observe is that, really the reason that these two functions share the same image is because V itself is in the column span of A, right? So an equivalent way to write this is that, if my mode bit is 0, I'm just going to sample some random V within the column span of A. And otherwise, if I want these images to have, if I want these functions to have disjoint images, I could just sample random V outside of the column span of A, okay? Right? In that case, the image of the 0 function is just the column span of A. The image of the 1 function is some shift of the column span, right? And because of the dimensions, right, sampling some random V outside of the span of A is essentially just sampling a random V, since the column span of A is going to be a very small component of the entire space, right? So, good. So this gives me a dual mode function, right? So we can check if R equals 0, again, these functions just have the same image, it's just the span of A. Whereas R equals 1, they have disjoint images with very high probability, right? Okay. As you might have already noticed, there's really no security here. Recall, like, really the only security property that we want is this mode indistinguishability property, that I can't distinguish whether my pair of functions has been sampled in the 0 mode or the 1 mode. But here it's really easy to tell just by simple linear algebra, right? I'm given A and V, I can check whether V is in the span of A, and that determines the mode. Okay, so to make this plausibly secure, we will just kind of appeal to the kind of techniques we covered earlier in this week and say, you know, what is LWE good for? In particular, it allows us to, like, hide a vector, or, you know, to take a vector in the span of A, add a little bit of noise, and suddenly it becomes indistinguishable from random, right? So let's suppose that instead of simply defining V to be in the span of A, we sample a little bit of noise and add that in order to define our vector V, right? So here I'm not really going to go, again, I'm not going to really go into the details of LWE and so on, but for now, let's just, or for the purpose of this talk, let's just recall that our error is going to be sampled from some distribution that is supported on, like, short elements, right? So each element of E, I'm going to sample in this range, let's say negative B to B, where B is much, much smaller than the modulus Q, okay? You know, but by doing this, this is the problem of distinguishing AS plus E, right, from a completely random V is exactly the LWE problem, okay? So now the mode indistinguishability has been reduced kind of immediately to the hardness of LWE. Okay. So we've actually introduced a new problem by adding this error. And the new problem is that when r equals 0 in this you know, in this first case, actually these functions no longer have the same image. Okay. And we can see that because, you know, if in the r equals 0 case, right, the image of the 0 function is still just the column span of A, whereas the image of the 1 function is the column span of A shifted by some short error E, right? So visually, right, the image of 0 of F0 is some lattice, right? Whereas the image of F1 is some, like, shifted lattice, okay? Does this make sense? And again, this shift here, the shift from blue to red is just because we're adding this short error vector. Okay. So the way to solve this problem is basically to do the following. So instead of just defining the output of the function to be the lattice point itself, or the shifted lattice point, we're going to allow the function to sample an output, essentially. Now these functions will be randomized, and they will kind of sample an output in some ball around that lattice point, okay? So in particular, we're going to allow F0 and F1 to sample, you know, to compute the function that we defined, but then add to it some random short vector E prime, okay? Where E prime is sampled, you know, each entry of E prime is sampled from some domain that is, you know, sufficiently larger than E, but still much, much smaller than the modulus Q. And so again, the effect that this has is that, right, so the output of F0, kind of this blue region, is going to be like, you know, these balls around these blue points, whereas the output of the 1 function are going to be these balls around the red points. And now you can see that at least most of the time, like the overlap of the images of these functions is quite high. So they basically overlap almost everywhere, right? Yeah.
Makes sense, but just a naive question. So in general, you would only see the function in either the 0 or the 1 mode, right? You never see them both together. So what stops you from using using an error to make the points overlap? You could just use the same error and make the points overlap and get the same lattice. I mean,
No,
usually
well,
we can't do that because it's insecure if you see both, but here I thought you'll only see one.
well, you see, you know, both these functions, right? But
you do see
sampled in
both
one
the
of these two
functions.
modes,
Okay.
right? So.
Oh, I see,
Yeah.
I see, yeah.
Yeah.
Okay,
So
good.
right, okay,
Good,
maybe it's a
got
little
it,
confusing.
got
This
it.
0 and 1
yeah,
are different
yeah,
than
yeah,
that.
yeah. Now I got it. Good.
Yeah. Okay. So so indeed you're going to see A and some V. But now I'm being a little bit loose with my definition of a function. Now I'm saying, okay, I'm going to allow my function to like sample some error and add it to the output. Okay. And so this is something that is in the literature called a noisy trapdoor claw-free function, when we kind of allow the function to like basically sample some error and add it to the output. But without going into any details, I'll just assert that like this type of TCF, this noisy TCF, just like works just as well as like the clean TCF that I used to construct the oblivious state preparation protocol. It'll just be, you know, correct up to some potentially negligible error. Like if we set these parameters appropriately, like Q to be like super polynomially larger than E prime, which is super polynomially larger than E, then you get all but negligible correctness. Okay. Okay. So this almost completes the construction. We have a DTCF, and we have security from LWE. The last thing is that we just need the existence of a trapdoor. Okay, and you know, basically, Shweta covered techniques for how to sample trapdoors in the lattice setting, and that's exactly what we're going to appeal to here. So without deriving the techniques again, I'll just kind of state the conclusion of that, which was that we can always sample, or there exists a procedure, this trap-gen procedure, for sampling a matrix A along with the trapdoor T. Right, so the key properties here are that this matrix A is just still statistically close to just a uniformly random matrix. But now it comes along with this let's say M by M matrix T that's in the left kernel of A, at least mod Q. Okay, so if I like left multiply A by T, I kill A, right? But the two other crucial properties of the trapdoor T is one, that it is short, okay, so each entry of T is itself a short element, and also that it's full rank, and you know, because of this condition, it can't possibly be full rank mod Q, but what we care about is that T is actually just full rank over the real numbers, okay? So the reason, and again, this was covered earlier in the week, but the reason such a T is quite useful is the following. So this capital T is going to be the trapdoor of the claw-free function. And we'll note that any vector in the image of these functions, you know, in particular has the form. It's A times something plus some small error. Yeah?
Sorry, maybe I didn't got the notation. You wrote T in range of minus B and B, and I just trying to figure out minus B and B, what kind of value is it?
Yeah.
Is it also matrices, but it's...
Yeah, good. So here, I just mean that T is an M by M matrix, where each entry of that matrix lives in this bound. It's between negative B and B. And I'm imagining B is some number that's like much smaller than Q.
Oh, thank you. Got it.
Okay. Yeah. So, yeah, I mean, why is such a trapdoor useful? Well, if I have an image of one of these functions, which is just some, you know, lattice vector that's shifted by some error, then all I have to do is I left multiply this vector by T, and I take the result mod Q, and, you know, we'll see that, you know, T times A equals 0, so that part disappears, and we're just left with T times E prime. And then since T is short and E prime is short, T times E prime mod Q is actually just the same as T times E prime over the reals, since there's no wraparound. And then we can use the fact that T is full rank to solve for the vector E prime. Okay? And, you know, given this vector, once we solve for E prime, we have everything, right? We can strip E prime off and then solve for X, okay? So this is just, I didn't want to kind of completely recapitulate how to do trapdoor sampling and all that. We saw that earlier this week, but this is just to say we can just use those techniques to kind of add a trapdoor to this, TCF construction, okay? All right. Yeah, any questions about this? This was kind of one of the further steps on our road, right? So now we understand that just from the LWE assumption, we can build these DTCFs, which in turn imply what we wanted, this blind delegation protocol. Yeah.
So if you could show the previous slide. So even if we have when we have the point is that once we have the E prime, we can recover the V, and from this we get those two pre-images, or no?
So, yeah, I'm imagining just like, maybe I didn't hear the full question, but in order to take, what we want to invert is eventually like the input to this function f, right? And so once we have the E prime, what we're left with is A times X. And so just by linear algebra, then we can recover X.
All right, thank you.
Yeah. Yeah. Oh,
so if R is 0, if R is 1.
Oh, good, right. So if R is 1, then yes, right, we have AX plus V plus E prime. But I can write this as A times, X plus S, parentheses X plus S, plus E prime. And so what I recover once I strip off E prime is X plus S. And, okay, good, so technically I should have include S as part of the trapdoor. Okay, yeah, I didn't actually write that, but we should also include S as part of the trapdoor because, yeah, that allows us to basically recover both pre-images. Once we recover one, we can get both. Okay, so this is the kind of like the roadmap we've covered so far, and then I do want to note actually, I was debating whether to put it in or not, but I think due to time, it's okay that I didn't. Just to say that this object of dual mode TCF has more than one instantiation. It has an instantiation for LWE, which we covered here in this week, but there's alternative ways to do post-quantum crypto, and one of them is based on isogenies over elliptic curves, which can be abstracted via this notion of a cryptographic group action. And it's also known that we can instantiate these TCFs from this other problem. So this is just to say that there's a variety, well, I guess two at this point, ways of constructing this from post-quantum assumptions. Okay. So it's not specific to LWE. Okay. So really this completes, if our goal was just to get a blind delegation protocol where all we care about is, we have a quantum server and a classical client, and they can interact as much as we want, and the classical client can run as much classical computation as they want, but we want to do blind delegation, then we're done, right? But I do want to cover the fact that we can kind of make this protocol, we can get kind of more properties out of this basic template. And in particular, we can use these techniques to construct something called a quantum fully homomorphic encryption scheme, a QFHE scheme, which really satisfies two additional properties. I actually have only one written here, but it's a minimally interactive version of blind delegation, right? So between the quantum cloud and a classical client, we only require two messages. So the client sends the description of the computation Q along with an encryption of their input, and they expect in return an encryption of the output Q of X. And the other property that we care about is that the client is somehow efficient. In other words, the scheme is compact. And what that means is that the communication size, so the size of this ciphertext and the size of this response are, doesn't grow with the size of the circuit queue, okay? So it turns out, actually, that in the same paper that introduced the idea of using trapdoor claw-free functions to do blind delegation, it was also noticed that these techniques could be pushed further in order to actually obtain a full-fledged quantum fully homomorphic encryption scheme, okay? And the central observation, which I will try to convey in more detail soon, is that there exists a classical FHE scheme where ciphertexts, so like encryptions of a bit R, under this particular classical FHE scheme, is already a dual mode TCF with mode R. So I can kind of view this, encryption of R either as an FHE ciphertext or as, a dual mode TCF function in mode R, okay? So let's try to see how this works and why it's useful. I mean, this will be a very brief overview, but it's based on this idea of dual regev encryption, okay? So I think I think the introduction to public key encryption from LWE here was based on regev encryption. This is just a dual variant of it, where the keygen algorithm, okay, for this encryption scheme just runs trapgen, okay, to obtain a public key A and a secret key that, and the secret key is just the trapdoor for A, okay. And then to encrypt a bit R, the ciphertext looks like the following. It's just an LWE instance, AS plus E, so you sample a random S and some error E. And then depending on the bit R, you either add this vector U or not. Okay, so this notation is saying like, if R is equal to 0, do nothing. If R equals 1, add this vector U. And this vector is some fixed public vector that is, with high probability outside of the span of A. Okay. Like in the very basic dual regev encryption, you could imagine U just being kind of like the all zeros vector and like 1 like Q over 2 entry at the end. I mean, there's various ways to do it, but okay. So the point here, which I won't show formally, but is that this basic scheme can actually be extended to support fully homomorphic operations, which is sometimes referred to the dual GSW scheme. And really the only change that we need is that U is an appropriate matrix. I mean, it's the gadget matrix that we saw, right? So if we take U to be the gadget matrix and extend the dimensions of S and E appropriately, this turns into a fully homomorphic encryption scheme, okay? But this is also exactly the construction of dual mode TCFs that we just saw, right? So if V, if I let my encryption of R be the vector V, then this this matrix A along with this vector V is exactly a dual mode TCF in mode R. This is exactly the construction we saw, right? If R is 0, it's just V is just AS plus E, so close to the column span of A. Whereas if R equals 1, this vector is like shifted by some fixed vector U that takes it outside of the span of A. Okay, so that's exactly the construction that we saw. Okay, so this is the central observation, and now how are we going to use this observation? Okay, so now this might be also just a good review to see, just to remind ourselves how this blind delegation protocol worked. But let's kind of walk through it again, right? So again, I'm going to first describe the interactive protocol again, and then show how it can kind of be collapsed to just 2 messages. So the client starts by sampling the one-time pad for their input and sends it over. The quantum server initializes their initial quantum state. And then we do our computation in layers, right? So the quantum server computes the first layer. The classical client does the poly one-time pad key updates. And now we do this oblivious phase correction, right? And we can kind of open up this black box a little bit now because we've seen actually like how to do it essentially. And what we've seen is that the server wants to apply this oblivious phase correction to their state psi1, and the client's input is R1. Okay, and for the clients to enable this phase correction, they will first sample a DTCF in mode R11. Okay, so the bit that we want to correct is the first bit of R1. So what the client does is it samples this DTCF in mode R11. And what comes out of this protocol, like if you recall kind of the structure of basically this protocol, is that the server ends up with the phase gate applied to their the controlled phase gate applied to their state psi1, potentially up to some phase flip error. So and the classical client receives these measurement results from the server. So basically what's happening in this box is now just basically a measurement that we saw a couple slides ago. The client gets the measurement results, and then using the trap door for the dual mode TCF, the client can recover what is this bit B1. Okay, so what was the Z error that resulted on the server's side? Okay, so this is just kind of opening up the black box of really the oblivious state preparation protocol, which was then used for phase correction, right? So this is what the protocol looks like. And then we can kind of just continue in layers again. One slight difference I want to point out, or slight, not really difference, but just some detail that we have to be aware of now, is that this bit B1 that the client obtains is incorporated into the one-time pad, right? Because this B1, we're imagining just incorporating this into the Z part of the quantum one-time pad, and so the client's operation has to also reflect that's happening. Okay. But this is then we repeat until we end up with the output, the just one-time padded output that can be recovered by the client. Okay. Again, so this is essentially just a reminder of how the blind protocol works. Just noting that we have this more specific way that we're thinking of doing it based on these DTCFs. Okay. Now, let's apply our the observation made by Mahadev, which is that this DTCF might as well just be a dual regev encryption of the bit. Okay. And moreover, when I say dual regev encryption, I even mean, let's say, a dual GSW encryption, like a fully homomorphic version of it. Okay. So I can treat the DTCF as just a dual regev ciphertext. So what does this allow me to do? Well, let's say that the client, rather than doing all of these updates in the clear, we'll just do all of these updates under the dual regev or the dual GSW encryption. So they could do this. There's no reason for them not to. So instead of just starting with R0 S0, they could start with an encrypted version of R0 S0. Update the poly one-time pad keys under the hood of the encryption, and then just derive from this encryption an encryption of the first bit. We can always assume the encryption is bit by bit. So just when it's time to do the oblivious phase correction, just take the encryption of the first bit and treat that as the dual mode trapdoor function, right? So okay, all of this can be done under the hood of a fully homomorphic encryption scheme, and at the very end, the client could just decrypt it in order to recover the output. And we could go even a step further. Let's suppose that that even the client wants to keep. Let's suppose that the client even wants to keep this trapdoor encrypted, right? They might as well instead of like using the trapdoor in the clear, you know, they could have just have an encrypted version of the trapdoor used to derive an encrypted version of this correction bit B1, and then, you know, use the encrypted B1 to, you know, finish their update of the encrypted poly one-time pad keys, right? So this, you know, in terms of functionality, this still works. All of these operations can be done under the hood of a fully homomorphic encryption scheme. And now, the whole reason for doing this is to say that, well, you know, if the client can now outsource all of this computation to the server, because if you're just given like these ciphertexts, you know, you're not learning anything about the underlying encrypted information, as in like you're still hiding what the poly one-time pad keys are. So what the client could have done is just, you know, sent the encryption of the original one-time pad along with an encryption of the trapdoor to the server, and the server by itself could just be doing all of this computation without any help from the client, okay? Does this make sense? So just like looking at this a little bit differently, right? This first message from the client, we could consider to be actually a QFHE ciphertext, you know? It contains a one-time padded input, a FHE, a classical FHE encryption of the one-time pad keys, along with a classical FHE encryption of, you know, its own trapdoor. Okay. And then, you know, given this information, a quantum machine can, you know, perform this entire slide without any help, right? You know, it can, on the one hand, kind of do these quantum operations. On the other hand, kind of in parallel, do these kind of classical FHE operations, and at the end of the day, end up with this final evaluated ciphertext. Yeah. Sorry. So the question was, are they all using the same secret key? I mean, it's the same case in classical FHE. It depends if you want like bounded or unbounded depth, right? So if you're okay with like, you know, some bounded depth, then you could do you know, you can encrypt the kind of this trap. You can encrypt the trapdoor under a fresh public key and so on. So you don't need circular security. But if you want to get unbounded depth, then you need to encrypt the trapdoor of the scheme under its own public key, which.
So if you want bounded depth, can you use the same key for all of them, or is insecure?
Oh, good. No, I think if you want, if you don't want to rely on circular security, yeah, you have to choose, I believe, just new keys each time. Yeah. Yeah, so kind of like good.
I think so, right? I don't see why you need new keys. I mean, within the, sorry, maybe could you repeat the question?
Yeah, so the problem here is that this trapdoor is a trapdoor corresponding to the, you know, the public parameters of this encryption scheme, that A matrix, right? So if I want to avoid encrypting the trapdoor under its own A matrix, I will have to basically do a key switching step at each of these
I mean, you could use multi-key FHE maybe. Anyway, yeah,
Perhaps,
I guess it's not important.
But yeah, no, if you want to, yeah. But again, if you are okay with encrypting this trapdoor under its own A matrix, then you just need one, right? Okay. Although then this, I mean, I don't think you're ever going to avoid like at least blowing this up by the depth here, right? By the number of phase corrections. Yeah. Okay. Okay, yeah, no, I think this is basically what I wanted to say about the QFHE. Is any other questions about this? Yeah.
Yeah, so I'm looking to all of this from the practical perspective. Have you managed to evaluate this on some simulator, maybe? Or do you have some simulators for this quantum homomorphic scheme, or this is just like theoretical result?
Yeah. As far as I'm aware, I don't know if anyone has tried to do any. I mean, yeah. At this point, it's just feasibility, like theoretical feasibility, right? So it's polynomial time in our model of kind of perfect quantum computation, but yeah.
Will we have a chance to hear about verifying? In particular, whether it is only client that can verify, or can third party verify the computation without decryption? Good.
No. So yeah, the next part of this talk is going to be all about verification, actually. So this kind of ends the part of the talk about blind delegation and QFHE. So the last thing I wanted to talk about exactly is how these techniques that we've already seen actually can be useful for devising classical client proofs of quantumness, so the ability to prove that you've done something quantum to a classical client. And then hopefully with some time I'll just say I'll spend like really a rough sketch of how to do verifiable delegation. So here we want to have the client outsource a computation to the server and be sure that they receive the correct answer back. Okay. So our discussion of verifiable schemes is going to start with the CHSH game, which is a really kind of a fundamental idea, protocol in quantum information, which is originally due to Klausler, Horn, Shimoni, and Holt. Okay, and here's the idea. So there's two parties, Alice and Bob. Okay, and we are under the assumption that they do not communicate with each other. Okay. So there's also a referee, which is not pictured. But what the referee does is it samples two random bits, X and Y. It sends X to Alice and Y to Bob. And then each of Alice and Bob responds with a single bit. And the referee determines that Alice and Bob have won this game if the XOR of their answers equals the AND of X and Y. Okay? So for now, let's just imagine everything is classical. Okay? Alice and Bob are classical. And let's try to understand what is the probability that Alice and Bob can win this game, okay? So here's a pretty stupid seeming strategy, right? What if Alice and Bob, no matter what, just answer with the bit 0, okay? Well, we'll see that actually the strategy wins with probability 3/4, right? And the reason is that if we sample two random bits and take their AND, it's only going to equal 1 with probability 1/4. So 3/4 of the time, the answer that they're looking for is just 0, and so they can just respond with 0, right? And in fact, so the question is whether this is optimal, and in fact it actually is, right, in this classical setting, okay? And one way the notation for writing this is that the classical value of this CHSH game is 3/4. This is like the optimal probability with which the parties can win. And it's like, just thinking through this a little bit, it's not hard to prove, but I actually do want to explicitly step through a proof of how you can show this classical optimality, because it will be useful later when we design the proof of quantumness, okay? So here's one way to prove that 3/4 is optimal. So the first thing we can do is let's fix any deterministic Alice strategy, okay? So in general, Alice and Bob can use some randomized strategy. Maybe they share some like random string. But in this classical setting, you can just say that any randomized strategy is really just kind of a probability distribution over deterministic strategies. So, if a randomized strategy achieves, some success probability. There must be some deterministic strategy in the support of that randomized strategy that also achieves at least that success probability. So without loss of generality, we can focus on deterministic strategies. Okay. So a deterministic Alice strategy, just, all it does is it assigns one bit, like an answer bit, if Alice receives the question 0, and it assigns a different bit if Alice receives the question 1. So if we fix this strategy, we can derive what is the winning condition given Bob's question, okay? So if Bob receives the question 0, right, he knows that A XOR B should be equal to 0. So he should respond with what Alice responds to on question X, okay? So if Bob receives the question 0, his answer should match Alice's answer. Otherwise, if Bob receives the question 1, we know that A XOR B is actually equal to X, okay? So what that means is that Bob's answer should be equal to X XOR Alice's answer, okay? This is all, there's nothing fancy going on here. But what we want to analyze is, like, what's the best thing that Bob can do? What's the best win probability that they can achieve? And there's two cases. Case 1 is that Alice's strategy is such that she always returns the same bit, no matter what her question is, okay? That's one possibility. In this case, and if Bob receives the question 0, we're in good shape because Bob knows exactly, this bit is always the same, so Bob knows exactly what answer to return, and they win with probability 1. On the other hand, if Bob receives the question 1, in order for them to win, right, this bit here, since this is fixed, this bit is kind of just depends exactly on what Alice's question was. However, due to the no communication assumption, Bob has no information at all about what Alice's question was. So X was sampled uniformly at random, so the best Bob can possibly do is win with probability 1/2. For them to win, Bob must guess Alice's question. There's no way around it. So if we, take the overall winning probability, because 0 is sampled with probability 1/2, 1 is sampled with probability 1/2, overall they'll win with probability 3/4. Okay. Now we can do the same analysis in the other case, which is where Alice has a different answer for each question. And in this case, this first, if Bob receives the 0 question, that's kind of the problematic case, because in this case, he has to guess exactly what Alice's question was, okay? And so you can see, either way, there's one case in which, like, in order to win, Bob has to guess what Alice's question was, okay? So this is a really long-winded way to kind of prove the optimality of this game, but the point that I want you to carry with you is that kind of the fundamental reason that this classical value of CHSH is stuck at 3/4, that they can't do better than 3/4, is because Bob has no information about Alice's question. Anything they try to do, you can see that, because Bob cannot guess the value of X, they cannot do better than 3/4, okay? All right. So, things get a little bit more interesting when we consider quantum strategies, in particular, quantum entangled strategies, okay? So now, we allow Alice and Bob to set up some joint, potentially entangled state. And then, when we start playing the game, we still enforce this non-communication assumption, but they could be entangled with each other, okay? So the question is, in this setting, can they do better than 3/4? And one difference that we'll see, or that is apparent, is that in this quantum setting, we can't do this sort of like averaging argument. Like it doesn't just suffice to consider deterministic strategies, because randomness could actually come from quantum measurement. Okay. So that's one difference, but does that actually translate to anything useful? And so the question is, what is the quantum value, which is usually denoted with a star, so omega star CHSH, okay? So it turns out that it's more than 3/4. Okay, so how does it work? Suppose Alice and Bob just start with a single EPR pair. This is like an Einstein-Podolsky-Rosen maximally entangled state. One way to write this state is it's a 0, 0 plus 1, 1, where like Alice has the A system and Bob has the B system. You can see that, you know, if you instead write this state in a different basis, like you write 0 is equal to, you know, plus plus minus, and 1 is equal to plus minus minus, you'll see that this state is exactly equal. It's the same state as if I had written it as plus 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 minus minus. Okay, so this is equivalent ways to write the same state. So I'll give you Alice's strategy, and then we'll kind of figure out what Bob should do in order to win the game with optimal probability. Okay, so here's Alice's strategy. If she receives question 0, she measures her qubit in the Hadamard basis. So she makes an X measurement, okay? Capital X measurement, right? If her question is 1, then she makes a standard basis measurement, capital Z measurement, and she, you know, lets her answer A be the bit that she measured, okay? So that's her strategy. So we can kind of pretend, you know, since Alice and Bob's operations are kind of local, we can always pretend that Alice acts first. It doesn't matter for the analysis. So let's pretend that Alice just acts first, and let's you know, figure out what Bob's view is, okay, after Alice acts, okay? So here's Bob's view. His state, his half of the EPR pair, has collapsed into one of four possibilities, okay? So if Alice's question was 0, she measured her state in the Hadamard basis, okay? And if she got the outcome A equals 0, then her state collapsed to the plus state, which means Bob's state also collapsed to the plus state. So Bob has the plus state if X is 0 and A equals 0. On the other hand, Bob has the minus state if Alice got a 1 outcome, okay? So if Alice's question was 0 and her answer was 1, then Bob's state has collapsed to the minus state. Okay. So similarly, if Alice's question was equal to 1, she measured her EPR pair in the standard basis, which means Bob's qubit has also collapsed to the standard basis, and, you know, depending on Alice's output bit, Bob's state has collapsed to either the 0 or the 1 state. Okay. So we know that this is what Bob has in his hands, right? He has one of these 4 states. Of course, he doesn't know which state it has collapsed to, but, you know, he has one of the 4 states, okay? So we can figure out kind of, you know, we can figure out visually maybe kind of what Bob should do, okay? So let's suppose that Bob's question is 0, okay? Well, in that case, you know, X and Y is equal to 0, so we know that Bob wants to answer, we know that we want Bob's answer to match Alice's answer, okay? So, you know, looking at what states Bob has, we can see that if Bob has either the plus or the 0 state, then we want him to return 0. Whereas if he has either the 1 or the minus state, we want him to return 1, right? Now, there's no perfect measurement he can make that kind of always, you know, that always assigns 0 to the plus or 0 state and always assigns 1 to the minus or 1 state. But we can do kind of the next best thing and like split the difference, okay? So we can have Bob kind of measure in this X plus Z basis, okay? And if he gets, you know, this outcome, he can assign that 0, and if he gets this outcome, he can assign that 1, okay? So essentially, he's kind of like saying, okay, if I either have the 0 or a plus state, I'm going to get, you know, something, you know, this is like pretty close to both the 0 and plus state. This outcome is pretty close to the 1 and minus state. So it's kind of somehow the optimal thing for him to do, right? Okay. Now, what if Bob's question was 1? Then you could see that, you know, what we want is that, you know, Bob's answer is equal to A XOR X, okay? So if he has the plus state or the 1 state, then AX or X is equal to 0. If he has the 0 or the minus state, then AX or X is equal to 1. So in a similar way, we could say, well, Bob should measure in this basis, the x minus z basis, and assign outcome 0 over here and outcome 1 over here. Okay. So and we'll let the bit measured, we'll let b be the bit measured. So I guess I should say that, I guess I forgot to say that this representation of like the 0, 1 plus and minus state comes from the block sphere that I had up earlier, but this is like just this is just like the xz plane of the block sphere. So kind of one dimension of the block sphere is missing from this picture. Okay, good. Does this make sense? Okay. All right. So so this strategy actually wins with better than 0.75 probability. And so why is that? We can just kind of do it by example. Suppose that x equals 0, a equals 0. So Bob had the plus state, and his question was 0. So he measured in this basis here. So they win when Bob observes the outcome 0. And to determine the probability that you observe this outcome when you measure this state in this basis, that is something that just depends only on the angle between these states, right? So the angle between this state and this state, you can use that to derive the probability that you achieve this outcome. And technically, you can calculate it by a cosine squared of the angle, which turns out is equal to approximately 0.85. Okay? So if Bob measures in this basis, he's going to get the right outcome with probability around 0.85. And it turns out any way you set this up, you'll see the same thing, right? To take another example, if Bob has the 0 state and he measures in this basis, he'll get, again, the correct outcome with probability 0.85. Okay. In any case, whatever the questions are, right, whatever the pair of questions are, you'll see that they win with probability 0.85. Okay. And the interesting thing about this is that it's bigger than the classical value of the CHSH game. And in fact, it was shown that this is tight. Cyril Sin, I think in 1980, showed that indeed this is the optimal value of the CHSH game. No quantum entangled strategy can do better than 0.85. Okay. Okay. So so this is really nice. This is something kind of really historical in the field of quantum information. And indeed, we can view this game, the CHSH game, as a proof of quantumness in some sense, right? Under the assumption that what we're testing is whether there exists like two non-communicating, or the assumption that we're interacting with two non-communicating provers, right? So if we run this game with two non-communicating classical provers, the best they can do is 0.75. But if we see that they're winning, say we repeat the game and we see that they're actually winning with probability 0.85, then we can be sure that actually there must be something quantum going on. So this is really a bona fide proof of quantumness under the assumption that we're testing two non-communicating provers. Okay, but what we're interested in is really the single prover setting, right? So we have a classical verifier that's interacting with a single quantum prover, and at the end of the protocol, we want the verifier to either accept or reject. Okay, where completeness tells us that there is some quantum polynomial time prover that causes the verifier to accept with some probability, let's say v plus epsilon, whereas no polynomial time classical prover can cause the verifier to accept with probability better than, say, v. So if we can achieve this completeness and soundness, then basically we have this like gap of epsilon, which is telling us that there really is, if the prover is winning with this larger probability v plus epsilon, then they really must be doing something quantum. Okay. All right. So the question is, can we design a proof of quantumness protocol in this single prover setting? And it's been known essentially that we can ever since the 90s. So for example, what about Shor's algorithm, right? Suppose the verifier just multiplies two large prime numbers and sends the results to the prover. Under the assumption that factoring is hard for classical machines, if the verifier receives the factorization back, then they, under that assumption, they can be sure that the prover was indeed quantum. Okay, so, Shor's algorithm also gives us a proof of quantumness. But there's a couple, but we want to kind of improve this idea along multiple axes. And so one is like, we want to perhaps generalize the assumptions under which we can achieve proofs of quantumness, right? So Shor's algorithm really relies specifically on the hardness of, specifically on the assumption that, factoring is hard for classical polynomial time machines. Maybe someone discovers a classical factoring algorithm, right? So we want to generalize the assumptions, and also we want to improve the efficiency, right? So it seems that running Shor's algorithm is going to take a huge feat of engineering, and it's unclear when that's going to happen. So the idea is, can we even achieve proofs of quantumness where the quantum prover, in order to win the game, is, say, much more efficient than implementing Shor's algorithm, right? Okay, so here's the idea. This is a very general template for achieving a proof of quantumness based on techniques we've already seen. So let's suppose the classical verifier samples a random bit and participates in an oblivious state preparation protocol with the prover. Okay, so we've already seen how to do oblivious state preparation. Okay, and we've seen that so the result, if the previously this bit was R, now I'm calling it X. So if the classical verifier inputs this bit X to the protocol, then the quantum prover, depending on the value of X, will either get a Hadamard basis state or a standard basis state. Okay, and the verifier learns via the bit A which state the prover received. This is just this oblivious state preparation protocol, which we've already covered. But the observation is that the view of the quantum prover at the end of this state preparation protocol is exactly Bob's view in the CHSH game. Okay, so now let's view X as essentially Alice's question, right? So if X equals 0, Bob received, one of these Hadamard basis states. Whereas if X equals 1, Bob received, Bob had in his hands one of these standard basis states. Okay, so we can view, X as being Alice's question, A as being Alice's answer, and then the state of the quantum prover's system as being identical to the state of Bob's system in the CHSH game. So to complete the proof of quantumness protocol, all we have to do is ask the Bob question. So now the classical verifier will sample a random Y, send it to the prover, and then the quantum prover will implement Bob's strategy from CHSH. So if Y equals 0, measure in the X plus Z basis. If Y equals 1, measure in the X minus Z basis, and return the resulting bit. And now the classical verifier will accept if the CHSH winning condition is satisfied. Okay, so I basically just described in some sense the CHSH game just in this like single prover format. Okay.
Question.
Yeah.
Again, it's a naive question. Why do we need to do the oblivious state preparation protocol? Like you could just run, like you're running the second phase, you could also just run the first phase, right?
Good, so that'll come up in the soundness analysis, right? But first let's just check completeness, right? The completeness parameter is about 0.85. Like, what a quantum prover can do is just follow Bob's strategy that we covered from CHSH, and just by the analysis, okay, first by the fact that this oblivious state preparation protocol is correct, and the analysis that we covered a couple slides ago, the prover will be able to cause the verifier to win with 0.85 probability. Okay. Now let's check soundness, and for soundness we only care about soundness against classical provers, right? We want to say that a classical prover in this protocol cannot cause the verifier to accept with probability greater than 0.75. And why is that? Well, the fundamental reason this is true is that the classical prover cannot, due to the security of the oblivious state preparation protocol, the classical prover cannot guess Alice's question X. This is exactly what the obliviousness of the state preparation protocol guarantees, that the classical prover gains no information about this input X. And going back to our kind of discussion of the classical value of the CHSH game, what we saw from that proof strategy was that, if Bob can't guess Alice's question with better than 1/2 probability, then any classical strategy gets stuck at 3/4. And so really the only thing you need, I mean, the non-locality assumption enforces that Bob can't guess Alice's question, but we can also enforce it cryptographically using the state preparation protocol. Okay.
If I'm a classical prover, then what is my output in the oblivious BB80 for state preparation? Because if I'm classical, I can't receive qubits.
Yeah. So in some sense, we don't care because we only care about proving soundness against the classical prover. So we don't care about completeness, meaning like, this protocol just has classical communication, right? So if there's a classical prover, in some sense, we don't care what they're doing in between the rounds as long as we can guarantee that they can't ultimately win this game with probability better than 3/4.
All right. So the arrow pointing to the left is a classical message.
Yes.
All right.
Yeah, so this is a little bit confusing, I guess, to have all of this quantum stuff still here when I have a classical prover, but really this was like something that could be implemented by a quantum prover. A classical prover obviously can't do that, but that's fine. Yeah. Good, and yeah, this is all just classical communication. Okay, and then the final point I wanted to make, right, is that this state preparation protocol, as we saw, can be implemented in just 2 classical messages using any dual mode TCF. So what this gives us is just a 4-message proof of quantumness protocol from some sort of general assumption, this DTCF. And in fact, if we only want, again, if we're only going for a proof of quantumness and we only want soundness against classical provers, we can even implement this DTCF using quantum insecure assumptions. We only actually need the TCF to be secure against classical computers. So that opens up other constructions from DDH and factoring and stuff. And so this really gives us a really general template for how to design a proof of quantumness protocol. And this template was, okay, so there's kind of a series of works, starting with Kahanamoku Meyer et al., that essentially all of these works basically implement this protocol, this template in different ways of implementing the state preparation protocol, but they all kind of fall under this general template.
Okay. Small question, so we have to repeat this a few times, right, then to...
Good. So yeah. So in the definition of a proof of quantumness, I just said, there's some epsilon gap between whether to accept or reject. If we want, we can kind of generically boost that gap to 1 minus negligible versus negligible if we just kind of repeat the protocol sequentially, say lambda times. Yeah.
So here's 0.1. So yeah, we just need.
Yeah, so if we repeat this protocol, say some security parameter number of times, we could get some,
So currently we are proving that someone can do some quantum operations, but we are not proving that they actually calculated our stuff using quantum computer.
Yeah, exactly. Yeah. So this is all we're proving so far is that the prover did something quantum. So there's this, good. So I'm not saying anything about verifiable computation. Yeah. Okay. Okay. So I will, given the time, I will honestly probably not really get to the verifiable computation part, which is fine. I was just anyways planning to really sketch it. But in the remaining minutes, I want to at least kind of build up to it a little bit so you can see kind of how to, very roughly how to take this basic idea and kind of generalize it. And so a really key tool that kind of vastly generalizes this approach is something called the KLVY compiler, due to Kalai, Lombardi, Vaikuntanathan, and Yang. And so they observed that this template that we saw here can be applied more generally than just to the CHSH game. So CHSH is just one example of a more general object that's studied in quantum information, which is called a non-local game. Okay? And any non-local game is defined by a distribution D and a predicate V. So it's the same setup, right? Alice and Bob, they might be entangled, but we enforce no communication. And the referee samples 2 questions from some distribution D, expects 2 answers. These might be more than 1 bit now. They could be arbitrary strings. And then applies some verification predicate based on the questions and answers. And this is just a general notion of a non-local game. So KLVY observed that it's not just the CHSH game, but really any non-local game can, in some sense, be compiled from this 2-prover setting into this single prover setting. Okay? And so this is how it's done, right? A single prover will begin by setting up the entanglement between Alice and Bob. The classical verifier, so now there's a single quantum prover that kind of implements both Alice and Bob strategies. The classical verifier begins by sampling these 2 questions. And then in the first half of the protocol, the classical verifier and the quantum prover will participate in some blind delegation of Alice's strategy. Okay? So the verifier will kind of input X to this delegation protocol. The prover will implement Alice's strategy, and the outcome, which is returned to the verifier, is going to be Alice's answer. But crucially, the quantum prover doesn't learn what the verifier's input is. Doesn't learn what the verifier's input X is, right? So after this is done to Alice's side, then the classical verifier just sends Bob's question in the clear. The quantum prover runs Bob's strategy, and then the verifier decides to accept or reject. Okay, so what KLVY in 22 actually showed, so they kind of proposed this compiler, and then what they showed is that this is kind of the completeness claim. A quantum prover can implement any quantum polynomial time 2-prover strategy for G. Okay, so and the kind of the success probability of the strategy carries over to the single prover setting. Okay, and then in terms of soundness, they were concerned with soundness against classical provers, and so what they showed is that for any classical prover in this single prover setting, they can only cause the verifier to accept with probability, maybe negligibly more than the classical value of the game. Okay. And the reason, I mean, basically what's happening is that this no communication assumption is being replaced by, on the one hand, Alice not knowing what Y is because she has to act first before the prover receives Y. And on the other hand, Bob not knowing what X is due to the blindness of this delegation protocol. Okay, so kind of on one side, this no communication assumption is being replaced by a computational assumption. But this is how we can compile it to just a single prover setting. And I should say, actually, that technically KLVY only considered QFHE in particular, like a 2-message delegation protocol. It should be able to be extended to kind of any blind delegation protocol, but just to be exact, their paper only considered FHE protocols.
But since the quantum prover simulates Alice and Bob in their head, nothing forces them to actually forward the second message to Bob. The prover can forward it to Alice.
Nothing forces, that's true, but all we care, okay, right? So on the one hand, we care about showing completeness, and in that setting, we just assume the prover's honestly doing the thing, right? But for soundness, I mean, this takes a proof, but the point is that whatever the quantum prover does, it can't beat the classical strategy of this game Essentially because, Bob is for the same reason as we kind of sketched for the CHSH compiler, because Bob cannot, guess what Alice's question was because it was hidden by the blind protocol. So it takes a proof, but the intuition is that this no communication assumption translates to, or I guess it's the other way around. The intuition is that this idea that Bob can't guess X and Alice can't guess Y is kind of enough to show that they can't do anything better than the optimal classical strategy in the two-prover setting, if that makes sense. Yeah.
So in the previous protocol we saw, we were really relying on this gap which is there in the CHSH game.
Yeah.
So obviously to instantiate this, you need a non-local game which has this gap, right?
Yeah. Yeah.
So what all non-local games are there? I mean, it's only as interesting as the functionality that the non-local game will give you a gap for.
Yeah, exactly. So this is what I'm coming to next. So maybe essentially what you're asking is this first bullet, like, okay, just using like a really simple CHSH game, like we already had simple proofs of quantumness. So what was the point of this generalization? I mean, there's a few points, right? I mean, it's just generalizing the idea is interesting, but the main reason that I wanted to discuss is that this gives us now some ability to potentially go beyond proofs of quantumness and try to address this question of verification of computation. Okay, so can we use this idea to actually test not only that the quantum prover is doing something quantum, but it's actually computing a quantum functionality correctly. So just to be clear, like in this setting, we have a quantum prover, a classical verifier. They both know the description of the circuit and the input. They communicate classically, and the verifier outputs a bit, right? So let's say that the output of this circuit is supposed to be a single bit. For completeness, we want that if the prover is honest, the verifier outputs the correct bit, Q of X. And for soundness, we want that no quantum polynomial time, potentially malicious quantum prover can force the verifier to output the wrong answer, 1 minus Q of X. Okay? They can force the verifier to abort, that's fine. We just don't want them to force the verifier to output the wrong answer. So this I will sketch pretty briefly, but the idea is that in the quantum information literature, kind of starting with this work of Reichert, Unger, and Vazirani, there's many follow-ups, and one particularly kind of a simple instantiation of these ideas is due to Grillo in 2017. But it's been known that given any, so BQP is a bounded, just think about it as a quantum polynomial time computation. So given any polynomial time quantum computation, Q of X, there does exist some non-local game G and some inverse polynomial gap epsilon, okay, such that if Q of X equals 0, then the optimal quantum value of the non-local game is at least V plus epsilon. Whereas if Q of X equals 1, then the optimal quantum value of the game is at most V. So there's this gap. So there's this gap in the game that determines, whether the output of this computation is 0 or 1. Okay, so I can kind of map every particular instance of a computation to a particular non-local game. Okay. So this is promising. We want to use this idea to then obtain verifiable, full-fledged verifiable delegation. There's kind of one extension that we need still of the KLVY compiler, and the idea is that so far I only kind of said that what KLVY proved is that their compiler preserves the classical value of the game. So they only kind of prove soundness against classical computers. But for verifiable delegation, we care about soundness against quantum provers. So we have to reason about, whether this KLVY compiler preserves even the quantum value, the quantum optimal value of the game. Okay, and so this is kind of something different. So if we return to the compiled CHSH game, for instance, this question boils down to, right, which we haven't answered yet, in this compiled setting, can any malicious quantum prover do better than the kind of non-local value of 0.85, okay? And this was proven to be false. Like it was proven that this does preserve, at least for the CHSH game, it preserves this value of 0.85. And this was proven in 2 concurrent works from last year. And just to give you, like, hopefully a little bit of intuition about what they actually showed, is, they prove something kind of even stronger than the fact that this preserves the quantum value. They prove a rigidity statement, okay, which is that, they show that any quantum polynomial time prover that interacts in this game, if it achieves, a value of 0.85 or potentially even higher, which, eventually they show it can't, but, for sake of contradiction, right, if any prover that achieves the probability of at least 0.85 must be using 2 anti-commuting measurements. Okay, so what does this mean? Well, any malicious prover, no matter what they do, we can always say, on their final question 0, they apply some measurement to return B. And if their final question is 1, they apply a different measurement to return B, okay? And then we can use something, basically, this linear algebra lemma called Jordan's lemma to basically take, to take these 2 operators that the prover is applying and, consider what these operators do in just these, like, 2-dimensional spaces. So kind of, in some sense, by linear algebra, let's say, it kind of suffices to look at just the 2-dimensional case, okay? And then what they can show is that any prover that, because the prover cannot guess the value of x, it really crucially relies on that, then no matter what the prover's, if the prover is accepted with probably 0.85, their measurements must be at a maximal 90-degree angle, okay? And so what this actually shows, so this is a really powerful statement, actually. It's saying that, if the classical verifier sees that the prover is winning with probability 0.85, it knows that up to some rotation, the prover is applying either a standard or a Hadamard basis measurement, depending on which question they received, okay? So somehow the verifier is able to be convinced that the prover's operations are actually 2 anti-commuting measurements, up to rotation, either a standard or Hadamard basis measurement. And this is called the rigidity. So, good. So I think in the interest of time, I will essentially skip the details of this, which I was anyways only planning to sketch. But yeah. So what I want to say, though, like at a very high level, is that you can use this rigidity argument to enforce the following, okay? So you can set up a game such that if we can be convinced that Bob is applying either standard or Hadamard basis measurements, then we can verify whether any particular computation is 0 or 1. And this basically relies on like a quantum version of circuit SAT, essentially. I mean, there's like a quantum analog of SAT, which is basically this local Hamiltonian problem. And if we can be sure that Bob is performing honest measurements, then we can kind of like outsource the verification for this quantum version of SAT, okay? And then once we have this non-local game, we can compile it into the single prover setting and, basically obtain the same guarantees. And again, this relies crucially again on the fact that we can test whether Bob is performing one of these 2 standard or Hadamard basis measurements, okay? So this is what this work of Natarajan and Zhang showed. They showed that this kind of general proof strategy, or this general like compilation strategy, can handle compiling non-local games that are powerful enough to implement kind of arbitrary computation. And you can rely on, again, blind delegation to ensure that the quantum soundness is preserved. Okay. So again, if you're kind of if you followed like the compilation, the CHSH game setting, you can kind of think of this as just, in some sense, a generalization of that strategy that handles you know, much more complicated types of non-local games. Okay.
So you're just telling us that, like, for any quantum circuit Q, there is such a non-local game, which, so this is non-trivial, hopefully, right? Like, I don't see why.
It's non-trivial. I mean, it goes through, yeah, it's certainly non-trivial. I mean, it goes through the, like I said, this like quantum version of SAT, like this this local Hamiltonian problem, and then, yeah, this was, I mean, the first work that showed this, I think, was that RUV work that I mentioned, and it has since been like simplified, but there's been a lot of work on exactly that, yeah. So. Good. Yeah, so let me just basically recap what we saw, because I think I'm, yeah, only a few minutes. Good, so on the one hand, we show that using post-quantum crypto, we can construct this notion of a trapdoor claw-free function. And yeah, so we can use this crypto in order to build what I call this like oblivious state preparation protocol. And once we have this, we can use that to build proofs of quantumness and blind delegation. And you know, as I kind of passed over in the end there, you can show that this ability to perform blind delegation via this non-local game approach can also give us full-fledged kind of verifiable delegation as well. So really, this kind of idea of oblivious state preparation is kind of the bridge that allows us to go from, you know, just post-quantum crypto to classical client quantum server protocols. So where we're just using classical communication to somehow get some kind of advantage over even the quantum server. Okay. And yeah, like philosophically, like what is this oblivious state preparation? It's really what it's allowing the client to do is to prepare a state on the server's system that is in one of two different bases, and the server doesn't know which basis that state is in. So one way to think about that is that it's really just all the client has to do is establish like an instance of the uncertainty principle on the quantum server's system. And pretty much, you know, what really sets quantum information apart from classical information is exactly the uncertainty principle, the fact that, you know, things, you can encode information in two different mutually incompatible bases. So what this is saying is if we can somehow design a way for a classical client to again kind of like set up an instance of the uncertainty principle on the server system, we can then bootstrap that ability to construct all of these desirable classical client protocols like blind, verifiable delegation, so on. Okay. Good. So this is really what I wanted to say. I'm going to skip over some. Oh yeah.
Am I correct that you mean two different bases per bit, or is it two different bases for an entire thing? Because per bit it's like unbreakable. For entire message that you could approximate.
Two different bases per bit. No, I really just mean. Well, it's kind of independent of whether I'm encoding a bit or a string, right? It's like as long as there's two different bases. Maybe I didn't understand the. Yeah.
If you have a string, then it's 2 to n in string length of different bases that you can have.
Oh yeah, but what I'm saying is that it suffices to just consider two different bases, right? So you really just like I'm just saying, as long as we can do this for like a single bit, then that can be bootstrapped to all of this on the right. Okay. hopefully that answers the question. Yeah.
Okay, let's thank the speaker. Do we have any questions to James? Oh, we have a question over there.
When you had this orange star that says they only consider two-step protocols, so what is the general state of this theorem or lemma?
Yeah,
so is it even easier for multiple steps? We just don't know how to or is it too complicated to discuss this?
Yeah, to be honest, I mean, it's just, as far as I understand from like reading the papers, like there's nothing preventing the more general, like it's pretty straightforward, I think, just to generalize what they have to protocols that allow for arbitrary interaction. It's just that they only prove the theorem for two-message protocols.
Okay.
That's, yeah.
Thanks.